So this is an example of conservation of mechanical energy, specifically dropping a ball. So consider a ball being dropped a distance y naught above the ground, and consider that where the initial condition is that it is a distance y naught above the ground, and it's also moving with some velocity v naught downwards. And then the final configuration, it has not yet hit the ground. It's in midair, and it's now at some height y1 above the ground, moving downwards with the velocity v1. So we know from our kinematic equations that v1 squared is equal to v naught squared plus 2 a sub y times delta y, which translates to v naught squared plus 2 times minus g. Here's my coordinate system. G is downward. Let me add that in here. G is downward. Y1 minus y naught describes delta y. And so if I distribute the minus 2g, I get v naught squared minus 2g y1 plus 2g y naught. This minus and this minus gives me a plus. And then I get all the subscript 1 terms on one side and all the subscript 0 terms on the other side, and I multiply everything by m divided by 2. So in other words, m over 2 will multiply each of these two terms on the left side of the equal sign and each of these two terms on the right side of the equal sign. That would give me mgy1 plus 1 half mv1 squared is equal to mgy0 plus 1 half mv1 squared. And so we are ignoring air resistance, but this is a statement of the conservation of mechanical energy for this ball. And again, just to repeat, I am ignoring air resistance. That is, we are ignoring the dissipation of mechanical energy and the resultant heating of M and the resulting increase of the energy of the air as a result of the ball falling through it. So as a specific example of that, say that you had a 1 kilogram ball and it was 5 meters above the ground and you dropped it. What would its speed be just before it hits the ground? Using conservation of energy, we could argue mgy0 plus 1 half mv0 squared is equal to mgy1 plus 1 half mv1 squared. Well, first of all, the masses cancel everywhere. The initial velocity v0 is 0, so this term disappears. Since it hits the ground, finally y1 is 0, so this term disappears. These two terms disappear, in other words. So that allows simplification of gy0 equals 1 half v1 squared. v1 is equal to the square root of 2 times g times y0, which, if g is taken to be 10 meters per second, that's 2 times 10 times 5. Square root of 100 meters squared per second squared is 10 meters per second. So granted, we could have done the same calculation with our kinematic equations, but what we will find is that this idea of energy and energy conservation allows us to solve problems that we could not solve before. And furthermore, these concepts remain valid in non-Newtonian physics. For example, in relativity, we find conservation of energy also exists, and in quantum mechanics as well. It goes beyond Newtonian physics.